In the beginning, there was nothing. Not darkness as we understand it, for darkness implies the absence of light. This was the absence of absence itself, not emptiness, for emptiness suggests a void waiting to be filled. This was before space existed to contain anything at all. Not silence, for silence requires the possibility of sound. This was a state beyond all human conception, beyond mathematics, beyond philosophy, beyond imagination. A condition so alien to our experience that language itself falters in its description. What came before our universe? This question has haunted humanity since we first gazed upward at the night sky. Ancient myths spoke of cosmic eggs, divine breath, or eternal cycles. Modern physics offers us quantum fluctuations, multiverses, and dimensional brains. But the truth remains hidden behind a cosmic veil that even our most advanced theories cannot yet penetrate with certainty. We stand at the edge of knowledge, peering into an abyss of possibility. Yet we can journey back, almost to the beginning, to the earliest moments of creation. Our cosmic voyage begins 13.8 billion years ago, when everything that would ever exist, every star, every planet, every living creature, every atom in your body, was compressed into a point infinitely small and infinitely dense. A singularity, where the laws of physics as we understand them break down completely. A mathematical point of infinite temperature, infinite density, and infinite potential. Then came the moment that would give birth to everything, not with a whisper, but with the most violent event in the history of existence. We call it the Big Bang, though it was neither big in the conventional sense, nor did it bang like an explosion in space. It was the birth of space itself, the birth of time, the birth of everything that would ever be. In an instant, almost immeasurably brief, less than a trillionth of a second, the universe expanded from smaller than the nucleus of an atom to the size of a galaxy. This phase, known as cosmic inflation, represents an expansion so rapid and violent that the human mind struggles to comprehend its scale. Space itself stretched faster than the speed of light, carrying energy with it, doubling in size at least 78 times in the blink of an eye. Why did this happen? What sparked this cosmic birth? Our mathematics suggests that quantum fluctuations, tiny ripples in energy fields, may have triggered this moment of creation. In the seemingly perfect nothingness before time, there existed the possibility of something. And in the realm of quantum mechanics, possibility inevitably becomes reality, given enough time, though time itself had not yet been born. As inflation ended, the energy that had driven this exponential expansion was converted into a seething plasma of fundamental particles. The temperature of this primordial universe defies imagination, tens of thousands of trillions of degrees. No solid matter could exist in such conditions. No atoms, not even the subatomic particles we recognize today. Only raw, pure energy and the most fundamental constituents of matter, flickering in and out of existence. The newborn universe was nothing like our familiar cosmos. The four fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, which today govern everything from the orbits of planets to the fusion in stars, from the electricity in your home to the biochemistry of your cells, existed as a single unified force in these first moments. As the universe expanded and cooled, these forces began to separate in a process physicists call symmetry breaking, like a perfect crystal shattering into distinct fragments. First, gravity separated, becoming the weakest but most far-reaching of the forces, destined to shape the largest structures in our universe. Then, the strong nuclear force broke away, eventually to become the glue-binding atomic nuclei together. The electromagnetic and weak nuclear forces remained unified a little longer as the electro-weak force before they too separated in another symmetry-breaking event. 1/1,000,000th of a second after the beginning, the universe had cooled enough for quarks and antiquarks to form, the most fundamental building blocks of matter as we understand it. These particles and their antimatter counterparts appeared and annihilated each other in an eternal dance of creation and destruction, releasing photons, particles of light, with each annihilation. For a brief moment, matter and antimatter existed in equal abundance, locked in a cosmic battle for supremacy. But then occurred one of the most fortunate asymmetries in cosmic history. Through processes we still don't fully understand, matter gained a slight advantage over antimatter. Perhaps just one extra particle of matter for every billion matter-antimatter pairs. This asymmetry, this cosmic accounting error in favor of existence, would prove crucial. As the universe continued to cool, most matter and antimatter annihilated each other. But that tiny surplus of matter particles, perhaps 1 in a billion, survived to form everything we see today. 1 second into the life of the universe, the temperature had fallen to about 10 billion degrees. Still unimaginably hot, but cool enough for the surviving quarks to bind together, forming protons and neutrons, the building blocks of atomic nuclei. The universe was still an opaque soup of particles, a plasma so dense that light could not travel freely. Photons bounced from one charged particle to another, trapped in a cosmic fog. Between 1 and 3 minutes after the Big Bang, the first elements began to form in a process called nucleosynthesis. The universe had cooled enough, to about 1 billion degrees, for protons and neutrons to fuse, creating the nuclei of the simplest elements. Hydrogen, single protons. Deuterium, a proton and a neutron. Helium, 2 protons and 2 neutrons. And traces of lithium. The proportions of these elements, roughly 75% hydrogen, 25% helium, and a tiny fraction of lithium, were locked in during these first 3 minutes and remain largely unchanged throughout the cosmos to this day. Yet still no atoms existed as we know them. The universe remained too hot, too energetic, for electrons to be captured by these newly formed nuclei. Free electrons scattered photons in all directions, keeping the universe opaque, a blazing fog of charged particles that would persist for hundreds of thousands of years. For the next 380,000 years, the universe continued its expansion and cooling. Stars did not yet exist. Galaxies had not yet formed. There was only this gradually cooling plasma, expanding in all directions. During this period, matter began to clump together under the influence of gravity, creating slight density variations, seeds that would eventually grow into the cosmic web of galaxies we see today. These density variations arose from quantum fluctuations present during inflation, now stretched to cosmic scales, the earliest origins of cosmic structure. As the temperature of the universe fell below 3,000 degrees Kelvin, about half the temperature of the sun's surface, a transformative event occurred. For the first time, the universe had cooled enough for electrons to be captured by atomic nuclei, forming the first complete atoms. This era is known as recombination, though combination would be more accurate, as these particles had never before been joined. This transition marked a profound change like the cosmos, with electrons now bound to nuclei instead of freely roaming. Photons, which had been constantly scattered by these charged particles, suddenly found themselves able to travel unimpeded through space. The universe, which had been opaque since its birth, became transparent in what astronomers call decoupling. The light released at this moment, the oldest light in existence, still travels through our universe today, having journeyed across space for 13.8 billion years. We detect it as the cosmic microwave background radiation, a faint glow that permeates all the space, visible in every direction. Originally emitted as visible and infrared light, this ancient radiation has been stretched by the expansion of the universe, shifting its wavelength into the microwave portion of the spectrum. This cosmic microwave background is remarkably uniform, varying in temperature by only about 1 part in 100,000 across the entire sky. These tiny variations, however, are precious clues to the universe's structure. They represent the slightly denser and less dense regions, that would eventually evolve into the cosmic web of galaxies, clusters, and superclusters that define our visible universe. The moment of decoupling marks the edge of our cosmic visibility. We cannot directly observe events before this time, as the universe was opaque to electromagnetic radiation. This surface of last scattering represents our observational horizon. The cosmic background radiation is as far back in time as we can see with light. With atoms now formed and light free to travel through space, the universe entered a new phase, the cosmic dark ages. No stars yet illuminated the void. No galaxies spiraled through the emptiness. The only light was the gradually fading afterglow of the Big Bang itself, stretched and cooled by the continuing expansion of space. Neutral hydrogen and helium atoms filled the cosmos, slowly being drawn together by gravity into ever larger structures. For millions of years, the universe would remain in darkness as gravity slowly did its work, drawing matter into denser regions. Eventually, these concentrations would become dense enough to collapse under their own weight, igniting the first stars and ending the cosmic dark ages. But that is another chapter in our cosmic story. The stage was now set. The cosmic canvas prepared, the fundamental laws of physics established, the basic building blocks of matter created. The universe had taken its first breath, released its first cry of light across the void, and begun its long journey toward complexity. Every element that would eventually form Earth, every particle that would one day be part of your body, was forged in this cosmic crucible or in the stars that would later form. We stand in awe before the magnitude of this beginning, this transition from nothingness to the foundations of everything we know, from a singularity of infinite potential to a universe of infinite possibility. The story of Earth, of life, of humanity itself is written in this cosmic history, a history that connects us directly to the very moment of creation. If you enjoyed this episode, make sure to hit that subscribe button and turn on the notification bell so you don't miss the next episode. Also, leave a comment with at least 8 words. Your feedback helps us grow the channel and create even better content for you. Thanks for watching, and we'll see you in the next episode.